The definition says the following. By the way, this came up in 1982. Definition says the following. By crystal we mean any solid having an essentially discrete diffraction diagram. And by aperiodic crystal we mean any solid in which three-dimensional lattice periodicity can be considered to be absent. Look at the beauty. You see, the definition first defines a crystal through the diffraction pattern. The diffraction is the basis for the definition of the crystal. Also, it is a very humble definition. It doesn't say a crystal is. No. It says by crystal we mean. Very soft definition. Any solid having an essentially discrete diffraction diagram. Very soft definition. Very mild definition. Very humble definition. And a humble scientist who is open is a good scientist. And the science of crystallography before was not like that. So, wonderful. A great paradigm shift in crystallography. What brought this shift? And the subject of my talk is really that. 1982 was the 70th birthday of crystallography, and this was the year in which quasi-periodic materials were discovered. In order to show you what happened in the day of the discovery, let me show you my logbook from that day. This is electron microscopy logbook from my laboratory. I was on sabbatical at NBS, National Bureau of Standards in Washington, one of the national laboratories. I can say only good words about national laboratories, which we don't have many in our country, but they have many in the United States. These are wonderful laboratories. And this is a page in the logbook, and you can see the date here up there. It's April 8, 1982, and the material I was studying was aluminum, 25 weight% manganese, and it was rapidly solidified ribbon. And I was studying it. Why did I do that? Why would I bother study such a material? Because the project that sponsored me wanted me to develop a new aluminum alloys for the United States Air Force, for the United States military. DARPA sponsored this project. They told me, actually the sponsor called me to talk to me, and he said the following: Danny, you gave us a wonderful proposal. I sponsor your proposal for 2 years. You do your sabbatical at NBS. But let me ask you a personal favor. He knew me, this person. Jake Jacobson is his name. He said, Danny, I know you. And I ask you, don't stick to what you propose. Just run wild. I mean, do whatever you want. I sponsor you to do whatever you want. I said, thank you very much, as if I wouldn't do it without you saying that. But that's a good way to sponsor a scientist. Yes, do something that you propose, but also run wild. I wish every sponsor would say that. That's a good way, because this is the way discoveries can be made. Okay, so let's look at this logbook. And what you can see here is this is the number of the plate in the electron microscope, plate number 1720, so you can imagine there are many pages before that. SAD does not mean that I was set that day, it only means that it's a selected area diffraction pattern. And this page was not meant to be seen by anybody but me. So this is like a shorthand. I write things to myself. The handwriting is terrible. I write in the dark, but in the light also my handwriting is terrible. So I took some more pictures, and then came picture number 1724. I will show it to you soon. 36K, meaning magnification of 36,000 times. And it's a bright field image in the electron microscope. And when I looked at this, there was something very strange, and I decided to take immediately a diffraction pattern. I took a diffraction pattern, and lo and behold, tenfold? You all know that tenfold is forbidden, as well as fivefold. It turns out that it's fivefold, really. But from the image I will show you, I could not know that. I had to do other experiment, fivefold. Anyway, so this was the picture. And what you see here is that each one is a grain. Each one, like this, is a single crystal. Okay? And so this is a polycrystalline material. And the size of each one of these is of the order of a micron or two. And you notice that some of the grains are very black. I mean, pitch black, this and this and this. So this is what drew my attention. I've never seen such crystals before, so black. What it means to the electron microscopy is because this is a bright field image, it means that crystal, that grain as we call it, diffracts heavily. So most of the intensity goes out from the image and through the objective aperture, only the transmitted beam goes, and the intensity of that transmitted beam is so weak that nothing goes through because of the diffraction. And I said, oh, wow, let's look at the diffraction pattern. And this is the diffraction pattern. This is the actual picture, the first picture. And let's see what we have here. You see, what's strange here are two things. Number one, I started to count the points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, cannot be. 1, 2. I spoke in Hebrew. I said, Ein chaya kazot. So I said 1, 2, 3, 4, 5, 10. And then I wrote tenfold. The other thing, which is strange here, that there is no periodicity. You see, if you take the distance from here to here, and you multiply it by 2, or any other integer, you get by 2, you get here. And there is no intensity here. There is no spot here. If you take this distance multiplied by 2, you arrive here. And there is nothing there. No periodicity, 10 or 5-fold rotational symmetry. Very strange. But based on my previous experience, I decided that what it can be is a twinned crystal. A twin is a defect in a crystal. Actually, it's a grain boundary, but a very special grain boundary, very special crystal boundary, as I will show you now. So the other diffraction patterns, that means the following. Let's say that this is the specimen in an electron microscope. So I take a diffraction pattern from this orientation, and then tilt it, and take diffraction pattern from this orientation, and tilt it this way. I can tilt it and rotate it each and every way I want. And so these are all the meaningful diffraction patterns that emerge from that crystal. And so what you have here is actually 5-fold, 5, 3, 2-fold, 3-fold, in another direction, 5, 2, and another 5. So this set of diffraction patterns define the crystal as being icosahedral in symmetry. So, and that's why we named this first crystal that was discovered the icosahedral phase. Now, a little anecdote. When I was studying for my master's degree at the Technion, I took the class of crystallography, and the teacher in the exam gave us a question, prove that 5-fold rotational symmetry cannot exist in crystals. And I did. I proved it, and I passed. Otherwise, I wouldn't be here. So now, but when he said crystal, he meant, of course, periodic crystal, because there were no other crystal. So here is a little proof for you to enjoy. You see, in order to prove it, there are other ways you can do that. In order to prove, I choose 2 atoms, P and Q, in the lattice, and I choose the 2 atoms that are closest together, the minimum distance between them. And that distance is this distance R. And now, if 5-fold rotational symmetry is allowed, then I should be able to rotate Q around P 5 times, and P around Q 5 times, and let's see what happens. So let's take Q and rotate it 1, 2, 3, here we go, 4 and 5, and we have Q prime. There should be an atom here, if 5-fold rotational symmetry is allowed. Also P around Q, 2, 3, 4, and 5, and there is P prime, and because of geometrical reasons, P prime, Q prime is closer together than PQ, which cannot be because I chose the closest atom in the structure. Here's one proof that 5-fold rotational symmetry cannot exist in crystals. However, there can exist pseudo 5-fold symmetry. And this can happen, and by the way, these pictures I took many years before the discovery, in the 70s, and it was so trivial to understand this, I didn't publish it. And later on, I found a group of Chinese scientists who published 5 or 10 papers on this picture alone. So I mean, you can do these things in science. But for me, it was very simple. This crystal exists in the aluminum-iron system, very abundant, and they are quite large. You can see them in optical microscope. And I chose this is especially little one. And what you see here actually are 10 single crystals joined together in such a way that they are twin-related. So this one here, let's do it up here. This one here is twin-related to this. And this one here is twin-related to this. And in between them, you have a twin boundary. 1, 2, here is 1, here is 1. These are the twin boundaries. For the non-crystallography manual, let me do it very simply. Let's assume that these are atomic planes. My fingers are atomic planes. And so and this is one crystal, and the orientation in the other crystal is like that. They form a mirror image. So these are twin-related. The twins is because they form a mirror image. And in between them, you have the twin boundary. That's all there is to it. Now, you can clearly understand that if you take a diffraction pattern from one single crystal, you have a periodic diffraction pattern. But if you take a diffraction pattern from all of them together, then you have 10 superimposed diffraction patterns, which are periodic, and obviously you will have a 10-fold rotation symmetry. So let's do that, and here is the picture. This is the actual picture I took from that actual crystal. And as you can see here, there is a 10-fold rotation symmetry, obviously. However, we know that it emerges from 10 different crystals, and if you want to see one of them, here's just one of them. Okay, and if you do 10 times that, then you get the diffraction pattern. So this is pseudo 10-fold diffraction, the pseudo 10-fold rotation symmetry. And here is one with 5 twins in diamond that I took years later, and we should skip the explanation of the sigma boundaries. And then, because I thought that these are a twinned crystal, I said, well, let's find the twins. That's all there is to it, right? Find the twins and forget it. So I was looking for the twins. In order to find the twins, I performed an experiment which is called dark field images, a series of dark field images in the electron microscope. And I don't think we have time to go into details how we do that, but it was meant to show the different twins. As I have shown you in the previous picture, you see clearly the different twins, but using many diffraction patterns, many diffraction spots to take the dark field images, I could not find the twins. And so I said, well, maybe the twins are too small below the resolution of the microscope. Maybe I'll do another experiment called convergent beam electron diffraction. When you do convergent beam electron diffraction in an electron microscope, what you do is you converge your beam onto a spot, onto the smallest spot you can, and take a diffraction pattern from that spot. And the spot, the minimum spot size on that microscope, Philips, it was a Philips 400 microscope, the minimum size was 400 angstroms, or 40 nanometers. And the diffraction pattern that emerges there was that. Everywhere I went on the crystal, what you do is, this is the beam, convergent beam, and you move your crystal under it. You move from grain to grain. It was always the same. And so down to 40 nanometers, no twins.